Ah, wonderful. Good, that's what I worried about. Excellent. Well, thank you for that wonderful presentation, Lana. And we now switch to the second colleague, that is Kaveh Razavi. And Kaveh also joined the Computer Engineering and Networks Laboratory like Lana, but he did so already in 2020 as a tenure-track assistant professor for secure systems engineering. And the reason we have his inaugural lecture today is, of course, due to the pandemic. So a few words on his background. Kaveh has a bachelor degree in mathematics, which he obtained at Sharif University of Technology in Iran. And obviously, while this was very theory-oriented, he has a love for and passion for engineering and practical aspects of computing. And he then had an opportunity to follow this passion when he received an excellent scholarship by the ETH Foundation. And the person who I understand is not entirely innocent in this happening is Timothy Roscoe. So, Mothi, thank you very much for making sure Kaveh found his way to ETH. So I think this is a wonderful demonstration of the fantastic effects that such scholarships can have. So Kaveh did his master's degree with Timothy Roscoe at the Computer Science Department on Operating Systems, and then went to Amsterdam to do a PhD on cloud computing with Thilo Kielman. And then after the PhD, he went on a postdoc at Amsterdam, became assistant professor at Amsterdam, and then we were lucky enough to poach him and convince him that ETH was an even nicer place to be at than Amsterdam. So despite his young age, Kaveh has already received many honors and awards. Most recently, the ERC Starting Grant, just a few months ago. Before that, in Holland, the Veni Grant, which is the most prestigious early career grant one can get. He's got several other grants with more than 1.5 million Swiss francs, 5 Pony Awards. I had to look it up since I'm completely naive about, well, pretty much anything, but certainly computer security. And according to Wikipedia, the Pony Awards recognize both excellence and incompetence in the field of information security. Now, in your case, Kaveh, I'm sure this is about excellence. He also got 9 Best Paper Awards, and talking of papers, his publication list is very impressive. And again, for a naive mind like me, who knows nothing about information security, it's striking that he seems to work on 2 things, either on tools, specifically hammers, or animals. So he's clearly an expert on hammers, so the articles are all about row hammers, throw hammers, and even surgical precision hammers. And on the animal side, I found papers on zebras and cats and squirrels and kangaroos. Amazing. And then for good measure, there's the miscellaneous section on feng shui and parmesan. So I now start to understand, Kaveh, what you mean when you said to me, I like to try new things all the time. So there's interesting reading ahead. And Kaveh, despite you having been at the department already for 2.5 years, and us enjoying your presence, it is really a wonderful occasion today to welcome you officially to the ITED. Welcome to our department, welcome to ETH. We very much look forward to having you for many, many years as a colleague. Welcome, Kaveh.
Great. Thanks for the very kind introduction, class. And thanks, everybody, for coming today. So I would like to talk for you about hardware security. But before doing that, I'd like to take you back 20, 25 years. Back then, when you wanted to connect to the internet, you had to use such a device, some of you remember, it's called a modem, and then you had to dial into a number, right? And then there, on the other side, would be an internet service provider where you had to authenticate with, and then you would get access to the internet. So here is me, when I was much, much younger, a teenager who got access to this amazing amount of information, right, when I would connect to the internet. And then, I could talk with like-minded people who were interested in the same sort of things. I was learning all the time. I really, really liked it. The problem, though, was that for me to get access to the internet, I had to buy one of these internet cards. And these internet cards, you would pay for a teenager a significant amount of money just to be able to access the internet, only for 1 or 2 hours a week. So yeah, internet was great, but I was not so happy that I could only use it for short periods of time at a time. So, being very much interested in computers, I started trying to understand how these things actually work. How do we actually get connected to the internet? Now, through the modem, you would get connected to an internet service provider or ISP through authentication with one of their servers, right? And these servers back then would run an operating system back then, Microsoft Windows 2000. Now, some of you may remember Windows 2000 had many, many critical security vulnerabilities. So, for example, one of these was the remote procedure call service of this Windows 2000, which had many security problems. So it was critical because it was possible to compromise a server that was running Microsoft Windows 2000 through this critical security vulnerability without any authentication. So once you would connect to the network, to the ISP, you would get access to all sorts of servers that you could then exploit and compromise using this issue. And then, if you would look around a little bit, you would find certain information such as username and passwords that would allow you to get infinite access to the internet, right? So this was great because then certain teenagers weren't limited by this hourly use of internet. Today, things are a bit different, right? So we are always connected. In about 10 years ago, there was this revolution of smartphones. We all have it, and they're always connected. And sometimes it's also easy to forget that we are always connected, right? And since we are always connected, we have started building critical services on top of the internet. So here I have some examples that I use, right? So I use my phone to pay, right, through the Twint app. I use Signal to communicate with my friends and family securely. And then sometimes, whenever I go to a new place, I use maps to find my way around, right? So these services are too important. So it would be a disaster if a teenager this day would compromise these services, right? So, and this is the topic of my research and the research of my group. We try to build and construct reliable and secure computing systems. Now, it is not anymore 2000, right? And there were a lot of effort to make sure that it is not so easy to compromise software anymore. And these days, it is still possible to compromise software, but it's not anymore somebody who doesn't have a lot of skill who can do that. You need to be a nation state and whatnot to be able to pull off such an attack. And I think the reason why it has become so much harder to compromise systems through software is because of three reasons, three directions. One of them is the fact that a lot of critical software that we run in our systems, such as the browser, depending on what you use, is now open source. So there are a lot of people who are always looking at the source and making sure that security vulnerabilities do not slip through. So the other, I think, advancement that we have made is automated security testing. So nowadays, every time a developer writes a line of code, there are these fleet of servers at software companies that provide a lot of input to make sure that these new lines of code that have been added to software does not introduce security problems. And if indeed a security problem is introduced, it is fixed before it is shipped to the end users. The other reason is these software updates that sometimes you receive every time every now and then you see that there is a request for you to update the software on your phone or your laptop, and oftentimes these updates carry fixes for some of the security vulnerabilities that have been found after the software has been shipped to the masses. So this is great, and because of all this scrutiny that people have been doing, now I think it is much, much harder to compromise systems through software. But software is not the only thing that makes up a computing system. So there is also the tangible part of a system, which is the hardware. And hardware, in comparison to software, has received much less scrutiny when it comes to security. And because of that, hardware is in a bad place when it comes to security. So I have two examples here for you, and these are areas that we have done research in the past. So the first one is the security of the CPU. It is like you could call it the brain of the computer. And what we have noticed by looking into this is that because of the increasing complexity over the decades, thanks to the Moore's law and all these transistors that we have been getting, information unfortunately leaks in ways that people do not obviously always expect. So here I have examples of certain vulnerabilities, some of which discovered by others, some of them discovered by us, and all of these vulnerabilities allow an attacker to leak sensitive information from another security domain on the system. So this is obviously problematic. The other, I would say, important component that we have in our system is DRAM, and this is where intermediate computation results are stored. And because of the increasing density, we have nowadays a lot of reliability problems. So it is not always guaranteed that the data that you write to your DRAM is the data that you read back. And so originally it was reported as a reliability problem, so we picked it up and saw basically what sort of security attacks you can do with this type of reliability issues. And then we found out that, for example, you could compromise systems over the cloud. Right? We even built an app that used these reliability problems to gain root on an Android phone. So you start from an app that doesn't have any privilege, right? And then without relying on any software problem, you could essentially compromise the phone, which is a big problem. And there is not much that software vendors can do to fix it, right? Because it is an issue inside hardware. And then, there were also other scenarios where we looked into networks are getting ever faster, and it is possible to access memory very, very quickly, which is what you need to trigger these reliability problems over the network. You could compromise systems that way as well. So what should we do? This is basically where we are putting our research effort trying to improve the security of hardware. And this direction, I call it open hardware security, but I mean really two things. I mean the security of open source hardware, which I will be soon talking about, and I believe that hardware security should be done in an open way, so that not only just the vendors can look at what they're doing, right? It would be basically a lot of people who can basically analyze this security or mitigations and try to understand if there are issues before you ship the product to the customer, because it tends to stay with them for a very long time. And so we are doing effort in three directions, and I'm going to give you some examples of research that we have been doing in these directions. So the first one is building support for hardware testing, very much like hardware security testing, very much like how we test software. I think we need to build more and more support to do security testing, automated security testing on hardware, to make sure that many of these issues we can actually detect and capture before we send the hardware for tape-out. So, and one example that I think we have done some work to improve the situation is DRAM. So once after these reliability issues were known to be exploitable, vendors said that they have now deployed mitigations, and this is not something that consumers should be worried about, right? So if you read beyond the technical terms, it essentially says that you can use the device like you were using the device before, and you will not trigger these reliability problems anymore. So which essentially meant that they had been deploying some proprietary and closed mitigations inside these DRAM devices, and they were stopping these reliability problems. So we started looking into what they have done. So we did a lot of reverse engineering that I will not talk for you about today. But essentially what we found out is that they had tuned their mitigations toward the access pattern that people had used in the past to trigger these reliability problems, these bit flips. So here we have found like 3 of these access patterns, and essentially these are the number of memory locations that you have to access at a given point in time to trigger this issue. And if you look at the frequency on which these addresses are accessed, we notice that they are all essentially accessed at around the same amount of time, same frequency. And so once you look inside the mitigations, you realize that, okay, they're doing something that we call, in computer science, frequent item count, right? And these are, if you want to do frequent item count precisely, this is expensive to do in hardware. So they're doing some sort of estimation of these frequent items. So what we did was building a testing tool that makes accesses to these addresses in a non-uniform way with different frequencies. And we built this tool, and then we ran it on 40 of the DDR devices, DDR4 devices that we had in our lab. And what we noticed is that we could, bit flips started resurfacing on all of these devices, right? So which is quite unfortunate, right? Because these devices tend to stay for a very long time. So this was a collaboration with Qualcomm, and we also later on worked with Oracle to get it deployed for them. So the hope is that now that there is this, the barriers for doing these tests are lowered, now there will be more testing, and hopefully this forces the vendors to basically make sure that the mitigations that they're deploying inside the devices are more secure. So this is one example, and I want to say one lesson that I learned while doing this research was that what the vendors say is not necessarily what you're going to get. Okay. Now another example which I find very exciting is open source, the security of open source hardware, and this is usually hardware is produced like in a closed way, so we don't know exactly how it works. But nowadays there is a push for open source hardware, and RISC-V is one of the examples of this open hardware. Here I have some examples of open source cores that have been developed over the years. And if you look at the later ones, they're starting to approach the complexity of some of the cores that we have on our computing devices, on our mobile phones, and so on. So this is the first time as academics that we have access to a complex piece of hardware design that allows us to do security analysis, right? So academically, I think this is quite exciting, but I think from a society point of view, it's also important now we could actually do security analysis to make sure that maybe 5 years or 10 years from now, when we have these processors in our computing devices, they're actually have gone through a more rigorous security testing than what we are seeing today with our commercial and closed CPUs. So, to give you one example of the effort that we are putting in this direction, so what we notice is that many of these security issues that I mentioned, we had different groups and us have discovered, they essentially are violating the microarchitectural confidentiality property, where sensitive information is leaking from one part of the microarchitecture to another where it shouldn't. So if we could somehow track this confidential information inside the microarchitecture, we should be able to detect when information leaks in places where it shouldn't. The problem with this tracking of confidential information, also known as taint tracking, is that it doesn't easily scale. And this is a place where we have been doing collaboration, and we've been doing collaboration with Intel, and we managed to build a system that we showed scales to complex RISC-V CPUs. So here I have one graph which shows when you apply this approach and do this analysis on a piece of hardware. On the left one, you see cores that are simpler, right? And on the right side, you see cores that are more complex. And the complex cores are, when it starts getting interesting from a security point of view. And on the y-axis, you can see the slowdown. So you will realize that, we're talking really, really slow, so things becoming 100 times slower. But this is not something that you will deploy in production, right? So you do this when you want to actually test. So it is fine if things are slow, if you can, do the analysis. It allows you to do the analysis. And what we realized when we did the analysis is, for example, on some of the cores, the more recent cores, some of these issues that actually plague commercial closed CPUs these days actually do start showing up in these more complex cores as well. Or in some cases, it doesn't, which is also good to know. So this is a collaboration with Intel, and from what I hear, they're interested to see whether they can integrate this inside their pipeline. Testing pipeline. So not only will this, help open source hardware, the hope is that maybe it will also help commercial hardware moving forward. So this was one direction where we are doing some work, and the other direction is looking into new reverse engineering technique. And this is like, sometimes this comes as a surprise that an academic group is doing reverse engineering, right? But I think for two reasons it sometimes makes sense to do reverse engineering. First of all, there are, as I said, hardware is oftentimes unfortunately closed, and we don't understand the security guarantees that the vendors claim they have. So it is good to do this reverse engineering to basically double check and verify that they indeed do what they say they do. The other reason to do this is to understand a little bit some of the parameters that are important when they have designed these mitigations for their hardware. And through this reverse engineering, we can learn enough about certain important properties of the hardware so that later on when we make similar mitigations for open hardware, as an example, we will not make similar mistakes. To give you an example, I would like to again talk about CPU issues. So 2018 was the year of CPU vulnerabilities. There were many that were discovered and basically became public. And the speculative execution class of attacks known as Spectre was one that is somewhat, I would say, more serious, and it is still staying with us to this day, so not so easy to fix. And also somewhat very expensive. So the mitigations that the vendor themselves had suggested software developers to do were very, very expensive. So, and instead, what some of the OS vendors did, such as Linux, was that we will convert all the offending indirect control transfers to return instructions. And because return instructions are speculated differently, then it means that it will be much, much harder, if not impossible, to exploit these return instructions. And this was very fast and very good to the point that even vendors such as AMD recommended that you use mitigations such as that one that convert instructions into return instructions. So for those of you who don't know, return instructions are essentially instructions that you execute when you make a function call. So it also allows you to do control transfers, but in a different way. So we were, of course, interested, right? So because returns looked somewhat like other indirect indirect control transfers, but a little bit differently, right? So we started looking into the behavior of these return instructions. And so typically what happens is that you have a certain state, and then this in your CPU, and this state is used by a prediction logic that tries to predict where your control transfer will go. Your CPUs these days, they execute tens, if not hundreds of instructions at any given point in time. So sometimes, it needs to make prediction on where the control flow of the program will go. And for returns, it was unclear for certain CPUs what is the relationship between these different microarchitectural buffers that are used for making this prediction. So we designed a lot of reverse engineering experiments. So if you've ever done reverse engineering, you know that this is a very painful process and not always an exact science. But at the end, after many trials and errors, we found out that it is possible. So if you have a victim return instruction, it is possible to create a specific collision from a different security domain inside one of these buffers, the branch target buffer in this example. And this allows you to create like masks such as this. So if you have an address that's sort of like when you calculate this function, it matches with a victim return instruction, for example, inside the kernel, then you can hijack the predicted destination of a return instruction. Okay? So this bypasses this mitigation that has been deployed on the systems for the past 4 or 5 years or so. So we wrote a paper on this and showed that you can use this to leak information on both Intel and AMD CPUs. And so what happened surrounding this was that AMD also came out and took this seriously, and they refer to this class of issues as branch type confusion. And for those of you who work in security or have heard about this, it sounds somewhat familiar, right? So in software we have type confusion vulnerabilities. And it is very funny that we are starting to see similar classes of issues now in hardware as well. So this is also one of the lessons that I learned, that hardware is more and more starting to look like software when we are talking about security vulnerabilities. The second lesson that I learned is that it is very difficult to mitigate hardware issues purely in software, right? So in certain cases, it is maybe worthwhile to invest slightly more resources to make sure that the mitigations that you actually end up deploying is actually secure. And this is, the third direction that we are spending some of our effort on, trying to design open mitigations where you could prove certain security guarantees that you get out of your mitigation. And this is where we are putting some effort beyond DRAM. And DRAM in particular is interesting because typically it is not so easy to update it and change its behavior using microcode updates. So it is something that you put in a system and then it tends to stay there for many, many years at a time. So if your mitigation is broken, suddenly the system could be compromised for many years to come. So, and here, we had done some reverse engineering in the past, and then we had noticed that, these reliability problems could be fixed at very specific points in time. And then, so we were thinking, okay, so even if you have a perfect mitigation, it means that only at very specific points, the rows that you could see corruption in would be fixed. So what you could do is, as an attacker, you could, access or call hammer one target, right? But now that the next point in time, one of these commands come, this target, the victims of this target could be fixed, right? But what you could do if you're an attacker, you could try to access some decoy rows, right? And then basically, this mitigation would fix these decoy rows instead of your target row. And you could repeat this again, so that you're essentially hammering your target, fooling the mitigation to pick the decoy instead of the target that you want to attack, right? So the question, of course, was, given this attack, how would you build one that is optimal, right? And this is where we started doing some formal modeling of the problem and try to prove some properties of an attack that would be optimal in this setting of this mitigation. And then this was a lot of work, but at the end the results were kind of interesting, right? So here I have a plot that shows essentially, given a perfect mitigation, it would still be possible to hammer a certain row for a certain number of times, right? So we call them like this is essentially this one row is flying under the radar. And this is great because it gives us like some bound. So even if you have an ideal mitigation, this is the security bound that you're going to get on your mitigation. And you could use it to build a mitigation that you prove is secure against this optimal attack. Since all the other attacks will increase the target by less than this amount, this means that you now have a mitigation that is secure against all possible attacks. So, and here I also learned something. I learned my respect for people who do formal work increased because I realized that this is actually quite hard. But in this case, I also think that this is quite necessary. So this is examples of our research into this direction. The hope is that, of course, we need to do more work in these directions to make sure that, the security of hardware becomes as good, if not better than software in the next 5 to 10 years. And I would like to, class already mentioned Moti's name, so thanks a lot for making it possible for me to come to ETH. But also I would like to thank my PhD supervisor who spent countless hours with me to help me with my research. And I would also like to give credits to my fantastic group here at ETH who is doing all the hard work that I just talked for you about. Thanks a lot for your attention, and I hope to meet you upstairs at the Docenten foyer for the apéro. Thanks.